Ah, welcome. I hope everyone had a great weekend. And this week, what we are going to do is really get into the heart of not just physics, but all science, the law of conservation of energy. I need to let you guys know that I am genuinely disappointed that I cannot be there in class to go over this with you, but I, again, can't let you leave my class without you at least seeing this. The Khan Academy assignment that I gave was talking about two different types of energy that we had already kind of discussed in the videos. We talked about kinetic energy and how you can use force to change kinetic energy. I never talked about that in the videos, but Sal Khan did explain it. Kinetic energy itself, and then gravitational potential energy. And what we're going to do today is understand how all of those energies connect and how they are all conserved. Now, this is a term. When I say conserve, what do I mean? I mean, if you conserve something, you're saving it. So when I say the law of conservation of energy, what I'm saying is that energy is essentially saved. It's not created, it's not destroyed, it's just transferred between different types. And again, the Newton's cradle, Newton's third law, all this is connected to the law of conservation of energy. I know we hit on this a little bit, but today I really want to get into the nitty-gritty of this. This is it. The law of conservation of energy says that energy cannot be created nor destroyed, only transferred between types of energy. So energy is never just appears, never just disappears. You just transfer it into different types of energy. So this is the list that we had the other week of types of energy. I went ahead and changed the first one, though, to what Sal Khan called gravitational potential energy. The reason that he did that, and a lot of college courses will go ahead and call it potential energy, gravitational potential energy, is because there's actually several different types of potential energy. I said generically that potential energy was energy that allowed something to move. It's not that it was causing it to move, but it would allow it to move. So if you hold your calculator up into the air, it has potential to fall. It's not moving, but it has potential to move. So there are other forms of potential energy. Chemical potential energy would be fat. If you have fat in your body, and we all have fat in our body, nobody has 0% body fat, provided that you're healthy and not malnourished. So let me clarify that. If you're not malnourished, you do not have 0% body fat. They say what, like 70%, 7 to 15% is like at a good kind of range of body fat to have. But again, every person's a little bit different, so don't worry about that. But fat within your body is stored energy. It's potential energy, because if you aren't eating enough calories, your body can go ahead and digest some of the fat that it has and release that energy. That's potential energy. It's chemical. It's potential chemical energy. So all I'm trying to say is that there's various forms of potential energy. The most common form is gravitational potential energy. And the reason why when I say potential energy, I really just mean this one, gravitational potential energy, because it's by far the most common. So from here on out, I know Sal Khan said GPE, gravitational potential energy. I'm just going to refer to it as potential energy, because for all intents and purposes for our class, that's what it is, just potential energy. You take college physics, you learn the other types, but for now, just there we go. Okay, let's get into this. Energy isn't created or destroyed, it's just destroyed, it's just transferred. Energy is just transferred among these types of energy. When you rub your hands together, you turn kinetic energy into thermal energy because you feel the heat. When you turn on your stove, you are burning gas to form flame, so you're doing chemical energy into thermal energy from the heat from the flame. Thermal energy goes into kinetic energy. If you're boiling water, you're causing the water molecules to move faster. Electrical energy, if you have a light on, you leave it on for too long, it converts some of the electrical energy into thermal energy. It turns the electricity creates heat. So all of these energies can transfer. What we're going to focus on primarily is how these two types of energies can transfer, gravitational potential energy and kinetic energy. These are the two that we're going to look at the most, but I want you to understand that if you look at a situation, energy is never disappears. It's always just transferred to a different type of energy. So, I got a lot of questions about the Khan Academy. And what I want to do real quick before I move on is just do a quick review of the gravitational potential energy questions that were in Khan Academy. All right, so I picked just a question at random. You may have seen this question, maybe you didn't see this question, I don't know. So it says a 2-kilogram toy car is released to the top of a frictionless track on the left and rolls off the track to the side of the right. The car starts to the height of 0.8, goes through a 0.5 meter diameter loop, and exits the ramp at a height of 0.25. What is the change? Change means delta, the car's gravitational potential energy from A to B. So this is all you really had to do. I know that Sal Khan said this, mg delta H. That's true. That you could use that equation. But if that equation wasn't making sense to you, this is what I would do. Calculate the PE here at point A, and then calculate the PE here at point B and just subtract. So you're going to use the MGH equation twice, and you're just going to subtract, because that's how you find the change. That is all you had to do. You had to just calculate the two PEs, and it said find the change, so you just find the difference. So what would that be? So this would be 2, 9.8, the height was 0.5, minus 2, 9.8, and the height was 0.25. So if I type that in my calculator, okay, I'm going to get 4.9. So it is point A. Oh, well, okay. So point A had a PE of 9.8. Point B had a PE of 4.9. Sorry. So what is the change from A to B? Physics, you always minus final minus initial. So you would minus 4.9 minus the 9.8, because technically from A to B, it's going down by 4.9. So the change would be negative 4.9 joules. You do the final spot minus the initial spot. Physics, all sides is always final minus initial. 4.9 minus 9.8. 4.9 joules. Okay? Just in case you were wondering, how could you get that without this? What Sal Khan was saying is mg, so 2 times 9.8, and then he said just subtract the heights. 0.25 minus 0.5 is negative 0.25. If you type that in your calculator, either way, you do it my way, you do it his way, you will get the same answer of the negative 4.9. So that threw a lot of people, but I just want to explain that real quick. Okay, law of conservation of energy. Energy cannot be created or destroyed, it's only transferred. So the total energy in an object equals the sum of all component energies. And I actually did mention this the other week. Sigma E, sum of energy, total energy. I will use sigma E, that means the sum of energy, or sometimes I'll just use TE for total energy. I'll use these interchangeably, I forget. Sometimes I just use one or the other, but just so you know, I want you to know both terms. They mean the same thing, sum of energy or total energy. So the sum of energy is potential plus kinetic, and then of course plus any other type of energy you have. But I said for the most part, we're just going to focus on this. So I can actually say that the total energy really equals this equation here. I didn't actually give you this equation the other day, but a lot of you were able to figure it out anyway. But I want to physically give you that equation just so you can see how this is going to work in the future. The total energy equals mgh, because PE is mgh, and KE is 1/2 mv squared. And then when you can use this equation when there's no other types of energy present. And for the most part, that's what we're going to do. So what is the total energy of a 2 kilogram basketball, 2 meters high, rolling 2 meters per second? This is basic. We did this already. All right, real simple. You can look through that if you're confused, but let's keep this moving. Okay, this is what the law of conservation of energy is essentially saying. Picture the situation. We have a boulder sitting on the top of a cliff. Right here. I'm saying that right here, the potential energy is 50, the kinetic energy is 0. And we know that the total energy never changes. So within this system, I know that the total energy is what you get when you add PE plus KE. So I know the total energy is 50 joules. But let's just say that the boulder falls. It was on the edge and it fell. And as it falls down, it's now less high. The height is decreased, therefore the potential energy is decreased. At this one point in time, so this is the same boulder, it's just at a different point in time, what is the kinetic energy? Well, I know the energy is not created or destroyed. So if I lose potential energy, it's got to go somewhere. In this case, it's going to go to kinetic energy. Because I know, in this case, the total energy never changes. It's just converted to a different form of energy. So I know that every single spot when the boulder is in the air, its total energy has to add up to 50. So let's just say it keeps falling, all right? Now at this point, I know that the kinetic energy is 38. What's the potential energy? Well, I know that these two energies must be added up to equal 50. There you go. Every spot has the same total energy, 50. Now, let's just say it's about to hit the ground. So its height is 0. What's its kinetic energy? 50, because it's got the same total energy. But here's the question. This is what happens. And this is where students get mixed up. They're like, but wait, then Bizzuto, so how does it have 50 joules of kinetic energy if it's hitting the ground? So where does the energy go when it hits the ground? It's then transferred. So what happens is, as the rock is falling, the rock is just transferring its energy from potential to kinetic. But when the rock hits the ground, it then transfers its energy to the ground. So then when it transfers its energy away from the rock into the ground, then it loses all its energy, but the energy didn't disappear. It was just transferred to a different object. So you have to be able to account for where all the energy goes. Most of the time, we're going to talk about energy transferring within one situation. Let's look at this again. Here we go. So here's a situation of a ball rolling down the hill. Okay, this is the same ball at 4 different points in time. Okay, we can just imagine we took 4 pictures of the ball rolling down, and here it is, spot 1, 2, 3, 4, 1, 2, 3, and 4. When I just look at this picture, which spot has the most potential energy? Well, potential energy depends on height. Which ball has the highest height? Spot 1. Spot 1 has the most PE and, mess that up. Spot 1 has the most potential energy and height. As the ball rolls down the hill, spot 4 is going to have the least PE and height. Okay? Because as it rolls down the hill, it loses height and therefore it loses potential energy. So how does kinetic energy roll into this? Well, let's think about it. If you drop a ball down the hill, as it's rolling down the hill, when is it going to be going the fastest? At the bottom. I think that's obvious. So at the bottom, we could say it has most velocity and KE. And then when is it going the slowest? At the top. At the top, it has the least V and KE. You could almost think its potential and kinetic energy as inversely proportional relationships, where you have a lot of PE, you have little KE. Where you have a lot of KE, you have a little PE. Because the energy is transferring. As the ball rolls down the hill, it loses height, so it's losing that energy. So where does it go? It goes to kinetic energy. So as the potential energy decreases, energy can't decrease. It just has to transfer its form. As the PE decreases, the KE increases, because what's happening is the energy is transferring from potential to kinetic as it rolls down the hill. The total energy never changes. So let's look at a situation like this. Here is a roller coaster with 4 different parts. So this is what I want to know. I'm going to go ahead. Let's rank the parts from most PE, KE, H, and V. We're going to rank it from most to least. Okay? So we got 4 spots. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. I want you to kind of think about this holistically. It's the same object, so that means no friction. All it's doing is turning its energy back and forth between potential and kinetic energy. So of these letters, which spot is the highest? A. So we can do the height really easily. A is the highest, and then just looking at it, D, that's what those little dotted lines mean. I can show you where they are. The wheels are the dotted line here, so it's higher than B. B would be the next highest, and then the lowest would be C. Okay? Now, height determines what type of energy? Potential. So if this is the order for height, this is also going to be the order for potential energy. Okay, you see how that works? Potential energy and height are connected. They will always be in the same order. Now, let's talk kinetic energy. I said that as potential energy is the biggest, kinetic energy is the lowest. So when do you have the most KE? When you have the least PE. Or conceptually think about it, when you're going to be going the fastest at the very bottom of the hill. The order for KE is going to be the exact opposite of PE. It's the exact opposite, because when you have the most PE, you have the least KE, and vice versa. And kinetic energy, KE, is connected to velocity. So if you know the KEs, you know the velocities. It is so important that you understand this concept as to how the energies relate to each other. I cannot stress this enough. As an object falls, it loses potential energy and gains kinetic energy. As an object falls, it loses height and gains velocity. I just said 2 sentences that essentially mean the same thing. I need you to see the interconnectedness of these variables and understand conceptually how the energies can change in a situation. Your work this week is going to be conceptual, where you're going to have to answer logical questions about what you see in terms of potential energy, kinetic energy, height, and velocity. There is another video to watch. Please watch the second video.